Hello everyone. In today's video we are going to go over some examples of vector calculus just to brush up on that. I know that we've been doing mainly conceptual stuff. So let's dive right in. So our first problem is going to be determining the surface area of this cone here. To find the surface area, what we want to do is we want to break up this surface into little tiny infinitesimal surfaces and then integrate across the entire surface to find the total surface. In this course, we typically define a little infinitesimal area as a vector. A vector whose direction is normal to the surface and it has a magnitude equal to a little infinitesimal patch or little infinitesimal area on the surface. We can call that our ds vector. And to find the total area, we just need to do this integration here. So if we have our ds vector here, we can dot it with our unit normal vector with the surface. So this would be basically a vector in hat is a vector that's normal to the surface and it has a magnitude of 1 because it's a unit vector. If we dot the unit vector with ds, that gives you the magnitude of the ds vector. So then if you integrate that and add up all the magnitudes of the little ds vectors, then that gives you the total area. So let's think about how we come up with an expression for the ds vector. First, what we have to decide is what coordinate system we're going to use. And our choice of coordinate system will either make our lives easier or harder. I am going to choose the spherical coordinate system in this problem because it will make our ds expression very simple. The reason is because this in hat vector here, in the spherical coordinate system, this in hat vector is simply theta hat. Theta hat equals in hat. And so that makes writing the ds vector much more simple than if we were to do like the Cartesian coordinate system. Let's walk through the steps of finding that ds vector in spherical coordinates. First, what you want to do is you want to sketch out a little differential or small patch on your surface and consider what the surface area of a little tiny patch like that would be in spherical coordinates. So first, let's look at the dimensions here. This dimension here, that would just be dr because it's a small distance and it's in the r direction in the spherical coordinate system. This distance here is a little more complicated. It would not be just d phi, because d phi is an angle, and we're wanting to find a distance. To find the distance, what you do is you project this patch down here, or this length, down to the xy plane here. And this little angle here, that would be a little differential d phi. And what we want, though, is we want the actual arc length of this right there. So we want this arc length. That arc length will be equal to d phi times this distance here. This distance here is equal to r times the sine of theta by geometry. This angle here is theta. So you've got that distance there, this d phi here. So the dimensions here, this little side right here, that'll be r sine of theta d phi. And that's the magnitude of your differential area. And then we know its direction. Its direction is it's in hat or theta hat. So that's our differential ds vector. So then you just multiply these two dimensions here, and that gives you your full ds vector. Now what we can do is you can dot your in hat vector with your ds vector, and that gives me this here. And now I can do my double integration to determine the total area. So for dr, I'm going from 0 to 5 because this distance here is 5. And then for d phi, I'm going from 0 to 2 pi because the cone goes all the way around. Oh, hey, Miwan, what's going on? You want to explain vector calculus to us? Vector calculus? You know about that? Do you? Do you? I don't think she does. So then I just go forward with the integration. It's pretty straightforward, but I've listed out the steps for you to walk yourself through. And keep in mind, you have to plug in theta equals pi over 3 right over here. So plug and chug, and I get 68.02 for my answer. All right, let's do a different example. Example involving calculating a line integral. So let's suppose you've got this quarter circle here between point 1 and point 2, and you have an electric field specified by this expression. And the question is, what is the integral of E dot dl going from point 1 to point 2? Just like the previous problem, we want to choose a coordinate system that will make the integration easy for us. So we're going to have to come up with an expression for the dl vector. So a little infinitesimally small line here, or vector, that and that is in line with this curve here. If we choose the cylindrical coordinate system, which is what I'm going to suggest, then I think it will be fairly easy to come up with an expression because this lies in the xy plane, and d phi is a measure of an angle in this direction here. But remember, we can't just use d phi because d phi is an angle. We need an actual distance. So what that actually becomes is we have to do r times d phi. So remember, in the cylindrical coordinate system, this distance here is r. And then you have a little differential angle d phi. So r d phi is actually going to be this arc length here. So that length there would actually be your dl vector. So once you have that length there, and yeah, it's going to be in the phi hat direction there. So that's pretty straightforward. Because we are working in the cylindrical coordinate system, we are going to have to convert our electric field expression, which is in a Cartesian coordinate system, to a cylindrical coordinate system. So in general, what we have to do is, if we have a vector A here in Cartesian form, and we want to convert it into a cylindrical form like this, we can use the following formulas here, and these are available in any standard vector calculus text. So in our example here, if we look at our electric field expression here, we can say that AX is equal to X, AY is equal to minus Y, and AZ is just equal to 0 because we have no Z hat component there. Another thing to remember also is that you will have to plug in place of X here, R cosine of phi and R sine of phi. That's just based on on geometry there. So if you plug and chug with all of that, and I'll let you work through some of the more of the details there, I get this expression for the electric field in cylindrical coordinates. So now you can just go ahead and plug this into your integral here. So this whole expression here, dotted with your dl expression, which is r d phi hat. So then you do that, that dot product multiplication, and I get this expression here. And then you can basically work through that integration, and I get the answer, an answer of 9. And remember that you have to set r equal to 3, because going back here, you can see that r is equal to 3 right there. So yeah, I'd encourage you to kind of go through the details, make sure it all checks out, but that should be the answer that you get. Okay, on to another example problem. Suppose you have a plane that is described by this equation. The problem we're going to try to solve is find a vector, a unit normal vector, going away from the origin from the plane described by this equation. So the general strategy that we will use for this is this. Step number 1, we're going to find 3 points that are satisfied, that satisfy this equation, or 3 points on the plane. Then what we can do is we can then, based on that, compute 2 vectors that lie in that plane. And then as a third step, if we take the cross product of these 2 vectors, based on the right-hand rule, we can find out what a vector normal to the plane is. And then from there, we can normalize the vector so that it has a magnitude of 1. So that's the general approach we'll be taking. So let's think about how we might find a single vector that is lying in an arbitrary plane here. So if you have a plane and you know 2 points that are lying on the surface of the plane here, so P1 and P2 there, if you want to find out a vector lying in this plane here, then all you have to do is take these 2 position vectors, subtract them, and you will get this vector here that lies in the plane there. That just goes back to, like, basic vector algebra that you've probably seen before, where if you have 2 vectors that are tied like tail to tail and you subtract them, the result of the subtraction is a vector that connects between the 2 heads of the original vectors there. So what we can do is, basically subtract the two position vectors, r1, r2, and r1, and that gives us a vector that lies in that plane there. So what we can then do to find points on the plane is, it really doesn't matter what points we choose, as long as we choose ones that satisfy this equation. So I just kind of look at it and pick 3 different points that when you plug these x, y, z values into this equation, it satisfies it. So you can work through that on your own and see that all of this checks out. So we have 3 points. We can then express the points in terms of position vectors. So here we can say r1 is just equal to 4z hat. So the 4 here. r2 is 8x hat. And r3, if we also include, a third point here, and you can see that I've sketched that out in blue, r3 is 16/3 y hat. And then you can also find a second vector in blue here second vector in blue, R3 minus R1. So I'm going to go ahead and call those, we're going to call this R2 minus R1 vector A and R3 minus R1 vector B. So these are the values then. You can do the subtraction here based on the values here, and you end up with the following two vectors that lie in the plane. I went ahead and sketched everything out here to make sure everything's clear. So here we have our three position vectors, R1, R2, and R3. And I went ahead and sketched those out. So R1 here is 4 z hat. R2, twice the distance here, is 8 x hat. And R3 is 16/3 y hat. And so the plane kind of lies right there on top of those three different points or positions. Our vector A points from 1 to 2, and our vector B points from 1 to 3 by doing that subtraction there. So now what you can see is if A and B lie in the plane, if we do A crossed with B, you can do the right-hand rule with this. I'm not going to, it's kind of hard for me to show it with my position here, but if you use the right-hand rule, A cross B will have a normal vector pointing away from the origin. So you do A cross B, and plugging and chugging, go into a textbook, do the A cross B on those two vectors we have, and you should get this value here. And you can go ahead and call that something else like vector C. So then if we want to find the normal unit vector, we just take this vector C and divide it by its magnitude so that it has a magnitude of 1. So I plug and chug with that, and I get this value here. So that's how we find the unit normal vector. So I hope some of those examples were helpful. There's definitely a lot more different problems we could tackle. It's definitely something you'll want to practice a lot with, and as we continue in this course, we will continue to use vector algebra and make much use of that. The key really is to practice and really understand how to think through the problems and come up and derive the differential areas and differential volumes and those sorts of things. Being able to think through the geometry, I think, is really key to being successful with all of this. Thanks for watching, and I will see you in the next video.